Linus Torvalds recently said that if you don't like Linux's relationship with AI, then fork it or just walk away. It sounds decisive, but for software and data engineers building production systems, this advice misses a critical engineering reality. You cannot simply rewrite the operating system to suit your needs because modern artificial intelligence inference relies on kernel-level features that act as physical interfaces to silicon hardware. Today, we connect Linus's ideological stance to the hard trade-offs of GPU passthrough, resource isolation, and why forking an OS can break your ability to talk to NVIDIA or AMD chips at all. The conflict here is not about open-source purity versus proprietary control in the abstract. It is a fundamental misunderstanding of how modern AI workloads interact with hardware drivers. When Linus suggests you fork Linux if it doesn't fit your workflow, he treats the operating system as code that can be rewritten without consequence. For an AI practitioner, however, the kernel is not just software. It is the only open, standardized interface deep enough to talk to modern silicon efficiently. Consider what happens when you try to run a large language model or generate video on current hardware. These tasks do not live in user space where applications normally operate. They require latency-critical components to move directly into kernel space to eliminate context, switching bottlenecks between your application and the hardware drivers. This requires specific scheduler optimizations, such as those found in aggressive distributions like CachyOS, which implement features like cgroups version 2 for precise resource isolation. These are not optional settings you can toggle on a new build. They are non-negotiable requirements for utilizing GPU or TPU accelerators effectively without wasting compute cycles. If an engineer decides to fork the Linux kernel to create a custom stack tailored specifically for their AI model, they immediately face a massive compatibility wall. The drivers that allow your software to talk to NVIDIA GPUs or AMD TPUs are tightly coupled with specific kernel interfaces and memory layouts. A forked environment risks breaking these connections during updates, leading to what practitioners call DKMS dances, where the operating system and hardware stop talking after a patch is applied. You might gain a cleaner codebase on paper, but you lose access to the driver ecosystem that makes your expensive hardware useful in production. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The stakes of this choice are visible when we look at how top-tier engineering teams actually select their infrastructure today. While some rolling release distributions offer newer kernel versions faster than standard enterprise options like Ubuntu, the latter remains the dominant choice for AI workloads not because it is boring, but because of its tight coupling with driver release cycles. Data from recent industry rankings shows that leading Linux distributions land GPU driver updates within hours of a vendor announcement. This speed ensures that when a new chip generation drops or a critical security patch arrives, your inference stack remains stable and functional without requiring manual intervention to rebuild kernel modules. A custom fork introduces significant risk into this timeline. Without deep upstream integration for features like GPU passthrough, every update cycle becomes a potential point of failure where the scheduler optimizations required for transformer execution are lost. This fragmentation forces teams to choose between maintaining their own version of the kernel or accepting that they cannot use the latest silicon efficiently. The emerging research on neurosymbolic kernels suggests that treating loadable kernel modules as active computation units is necessary for future AI. But this approach requires a unified codebase to maintain stability across different silicon vendors. This reality highlights a gap in how many developers are trained regarding hardware dependencies. Studies observing specialized training programs over 3 years reveal that while students possess strong coding fundamentals at the bachelor level, they often fail to grasp these specific kernel-level requirements. They assume an operating system is just a platform where code runs, not realizing that without specific features like cgroups v2 and optimized memory layouts for KV cache management, their application cannot access the parallel processing power of modern GPUs efficiently. This educational gap leads many engineers to believe they can simply fix the OS on their own terms when in fact, the hardware dictates the software constraints. The choice facing AI teams today is not between two open-source options where one is better than the other ideologically. It is a trade-off between a fragmented ecosystem where tooling breaks with every update versus a unified stack that guarantees hardware access even if it means adhering to upstream release schedules and vendor-specific driver requirements. Linus's dismissal of this complexity ignores that you cannot fork an OS without breaking your ability to talk to NVIDIA or AMD chips reliably in a production environment. The kernel provides the only open interface that allows diverse software stacks to communicate with proprietary silicon efficiently, but it demands strict adherence to its architecture rather than radical rewrites for niche use cases. For professionals making infrastructure decisions, this means prioritizing distributions with proven support for essential features over those promising cleaner codebases if they lack upstream integration for critical hardware interfaces. When evaluating AI infrastructure, the metric of success is not how much you can change the kernel to fit your preferences, but whether that stack guarantees your model will run on the specific hardware you bought without constant friction or downtime. The dominance of Linux in this space isn't ideological. It is an engineering necessity born from the need for a stable bridge between software logic and physical compute resources. In the end, Linus treats the operating system as code you can rewrite to suit your needs, but AI engineers must treat the kernel as a physical interface to silicon that cannot be easily rewritten without losing their GPU connection entirely. The path forward requires respecting these deep hardware dependencies rather than assuming they are optional software features that can be forked away at will. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.